Okay, girls, so we'll continue. We have this extra question, so I hope like you read it or you write it on a piece of paper and you try to answer it for next time. It's very easy. Okay, so what happens if you cut a magnet in a half? Part A, you get one magnet with only a north pole and one magnet with only a south pole. B, you get two smaller magnets, each one with its own north and south poles. Part C, you get two unmagnetized pieces. Part D, you get one magnet with two north poles and one magnet with two south poles. Okay, so I want the answer the next time. Now we will start with section 2, which is very important. Its title is Magnetism from Electric Currents. Okay, so first we will watch this video together.
From Science Buddies. In this video, we'll provide a brief introduction to magnetism. If you've ever played with magnets, you've probably noticed that you can use them to pick up metal materials, but not other materials like rubber, wood, styrofoam, or paper. This is because certain metals, primarily iron, nickel, and cobalt, have magnetic properties, but it's important to remember that not all metals are magnetic. For example, here on the right, most of the coins are actually made of copper, so along with this piece of copper wire, the magnet actually cannot pick them up, while it can easily pick up the paper clips and screws which contain high amounts of iron. Every magnet has two poles, a north pole and a south pole. When you bring two magnets close together, the opposite poles will attract or pull each other together. Here you can see a north and south pole pulling each other together. If you bring two similar poles, meaning two north or two south poles together, they will push each other apart. Here you can see one magnet pushing another magnet away without actually touching it, as two north poles are brought close together. If you flip the magnet around, the south pole will attract the north pole. You can do the same thing, starting out with two south poles, which you can see here will repel each other just like the two north poles did. You can push the magnet without touching it, and then if you flip it around, the north pole will attract the south pole. Magnets can push or pull on each other because every magnet is surrounded by an invisible magnetic field. We represent the magnetic field.
So here, girls, we are not till now. There is nothing new. Okay, it's just revision about the first section. Okay, so here I think the magnetic field around the permanent magnet is very clear. Okay, so you can see here how the lines are very close to each other, here and here near the poles, because here we have the strongest magnetic field. Okay, and here you can see how the field lines are far from each other, indicating a weaker magnetic field. Okay, so these lines, they all form what closed loops, as we said. So this drawing, please, you have to practice it. Okay,
with magnetic field lines that you can see here. Remember that every magnet has a north pole and a south pole. The magnetic field lines point from the north pole to the south pole, and the magnetic field is strongest where these lines are bunched closely together. Even though a magnetic field is invisible and you can't see it, it can still create a force on other magnetic objects, and you can detect it using a compass. A compass is a small bar magnet that is mounted on a pivot and is free to rotate. When there are no other magnets nearby, a compass will always align in the same direction. This is because the Earth actually has its own magnetic field. So since the compass is a magnet, it will...
So here, girls, you can notice that whatever you do with the compass, if you shake it, you move it, the needle will stay in the same direction. Why? Because here the needle, it's aligned with the Earth magnetic field. Okay, since no magnet around this compass, no magnet is affecting it. So see, no magnet around this compass. So this compass, it's not affected by any magnet around it. So therefore, it's affected by what? It's affected by the Earth magnetic field.
Earth's magnetic field when there are no other magnets nearby to disturb it. However, if you bring another magnet nearby, its magnetic field can override the Earth's magnetic field and affect the direction that the compass points. Now, watch what happens when I bring the compass close to a magnet. You'll notice that the white part of the compass needle is always attracted to the magnet's south pole, and the red part of the compass needle is always attracted to the magnet's north pole. Remember that this is because the compass itself is a magnet with north and south poles, and that opposite poles attract. The compass always aligns with the direction of the nearby magnetic field. You can see that in this image where each compass.
So girls, for sure, what do you think? In this compass, this needle, the one which is colored red here, it is the south, okay, because it's attracted to north. And the one which is white here, it is the north, because it's repelled from the north, okay. So some compasses we have like the red one, it's south, and the blue and white one is the south. It will be given for sure.
Is aligned in a different direction depending on its location. This is because the magnetic field lines curve around the magnet as you saw in the previous image, and each compass lines up with the magnetic field lines at its particular location. Another way to see the magnetic field is to use iron filings. Here you can see that if I cover a magnet with a sheet of paper and then sprinkle on tiny bits of iron filings, they will gradually take the shape of the magnetic field. This becomes more and more apparent as I sprinkle on more of the iron filings and shake the paper slightly to let them line up and take the shape of the magnetic field line. In this video, there's some white space around the magnet because the magnetic field is so strong that it pulls the iron filings in all the way to the magnet. Here's another example image that shows the complete magnetic field around the magnet using iron filings. There is also a relationship between electricity.
Okay, so the previous part was all of it revision about section 1. Now we will start with our part for section 2. So see, what do we have here? We have a battery, and what do we have here? We have a compass. So we are going to do something with the battery. Let's see.
In magnetism. Here you see a battery which stores electrical energy next to a compass. You can see that when I move the compass around, its alignment doesn't change, indicating that it's just aligned with the Earth's magnetic field. However, watch what happens if I connect a wire to the battery's terminals. This causes electrical current, or the movement of electrical charge, to flow from one terminal to the other. Now, when I move the compass near the wire, its direction changes. This is because moving electrical charge generates a magnetic field.
Okay, so stay with me. So girls, we said if the compass is alone with nothing around it, no magnet, okay, the compass will align with the Earth magnetic field, right? The north of the compass will point toward the north geographic. Between brackets, it means it's attracted to the south magnetic, okay? So this in case no magnet is disturbing our compass. But we said, as you saw in the previous part of the video, if we bring a magnet near the compass will align with the magnetic field of this magnet, because the magnet now is very close to our compass, so it will disturb it, it will affect it. Okay. But now, as you can see, we have a compass and we don't have any magnet beside it, but we have something else. We have a battery. Okay, at the beginning, when the battery is just like alone with no wires connected, nothing happened to the compass. But when you place or you connect a wire across the terminals of this battery, we can see that the needle of the compass moves or deflects. What means deflects? Deflects, it means it rotates, okay, from its original direction. So why it deflects? So here is the new idea. So when here you connect the wires across the battery, what do we know, girls? For sure the electrons, they will flow through the wire. So we have electric charge flowing through the wire. So this electric charge, so we can, girls, deduce that this electric charges are producing magnetic field, because a needle of a compass can rotate only under the influence of magnetic field. And here, so it rotates, so we can conclude that there is a magnetic field produced, because only the magnetic field can cause the needle of a compass to move, to rotate, to deflect. Okay, so since here the compass needle deflects, moves, okay, it means there is a magnetic field produced. So this magnetic field produced by what? It's produced by the electric charges flowing through this wire. So this is known as Ørsted experiment. See, we will continue here. So Ørsted experiment, Hans Christian Ørsted discovered in 1820 that an electric current near a compass causes the compass needle to be deflected, to move from its original direction. Ørsted's experiment showed that every electric current has a magnetic field surrounding it. So what he did, see? So he just laid a wire, okay, this is a wire connected to source of voltage. We have a power supply or battery or whatever. So when we connect, so we learned in electricity in the previous chapter that when you connect a wire to a battery, the electrons, they will move from the negative terminal through the wire to the positive terminal. So we have motion of electrons, it means we have electric current. We have electric current. So I will remind you, electric current, it is the amount of charges moving per second. Okay, so it is the flow of electrons. Once you have electrons that are flowing, we say that we have electricity, we have electric current. Okay, so the electric current is flowing, but here still it's off. Okay, when it's off, we see that the compass needle, it just aligned with what? With the Earth magnetic field. Okay, it shows us north from the south of Earth geographic poles. Okay, but when we turn it on, you will see that when we turn it on, we will see together that the compass needle will change direction. Okay, so Ørsted laid a wire across the top of a small compass, okay, and connected the ends of this wire to a complete electrical circuit as shown here. He had expected that the needle will point toward the wire or in the same direction of the current in the wire. He expected that the needle will stay in the same direction of the wire, or it goes like in the same direction of a flow of electrons. The electrons are flowing like this, so he expected that the needle will be the same direction of a flow of electrons, okay, like this. But he was amazed to see that when he turned on the power supply, the needle turned how? Like perpendicularly to the wire. Okay, perpendicularly to the wire. Okay, so here, first of all, we have to analyze the situation together. Pay attention with me, girls. Compass alone, with no magnet, with nothing around it, it will align with the Earth magnetic field only. Okay, but when you bring beside it a magnet, okay, it will be affected by this magnet. Okay, so the north will turn toward the south of this magnet that you brought it near. Okay, so it will align with the magnetic field of this magnet. Okay, طب here I don't have any magnet, I don't have anything, but what do I have? I have wire connected to a battery or power supply. I have wire carrying what? Current. يعني I have wire inside it, I have current, I have electrons moving. So when I have wire carrying current, okay, I see that the needle deflects. Needle deflects, it means that there is a magnetic field, because only the magnetic field can cause the needle to deflect. Only. Okay, so needle deflects, it means that there is a magnetic field. So here we can conclude that an electric current produce what? Magnetic field. So this is the first point in this lesson. So electric current or a wire carrying current, electric current produces a magnetic field, because we can demonstrate this using this experiment. Okay, so now, so we proved, girls, that a wire that is carrying, this is the wire, okay, a wire that is carrying current, it produces what? Magnetic field. Now we want to see what is the shape of this magnetic field. In order to see what is the shape of this magnetic field, we will do a very simple experiment. We will place here like this wire which is carrying current. Okay, electrons are flowing in this wire because this wire is connected to a power supply. Okay, we can put it inside a cardboard, okay, that has a hole here, and we can sprinkle on this cardboard what, girls? We can sprinkle iron filings. So because the iron filings are made of iron for sure, which is a magnetic material, which can be, what means magnetic material? Magnetic material are the materials that can be attracted by a magnet, right? Okay, that can be attracted by a magnetic field. Okay, it's not necessary to have only magnet. Okay, we can have magnetic field. Here I don't have magnet, but I have magnetic field, which is produced by what? By the wire carrying current, by the electric current inside this wire. Okay, so when you sprinkle iron filings, you will see that these iron filings will make the shape of circles. We call them concentric circles. Why we call them concentric circles? Because these circles like are around the center or around the wire that is carrying current. So if a compass needle turns when placed near a wire carrying current, it must be the result of magnetic field. So this point, we talked about it already. So this is the first point I told you in this section. So whenever we have electric current, this electric current will produce what? Produce magnetic field. How can we demonstrate this? We can demonstrate it by placing a compass near it, because if we place a compass near it, the compass needle will rotate, will deflect. Since it deflects or it rotates, it must be the result of magnetic field created by the current. Okay, so here I can ask till now two questions. Okay, the first question can be like, is electric current produce magnetic field? So for sure you will say, does electric current produce a magnetic field? So for sure you will say yes, it produces it. So I can ask you how can you demonstrate this? How can you prove that an electric current produces magnetic field? And your answer should be by using a compass, by bringing a compass near a wire that carries current. The compass needle deflects, so since it deflects, there must be a magnetic field that causes it to deflect. So we can conclude that the electric current produces magnetic field. Okay, how to show the shape? The third question, how can you show the shape of this magnetic field? So this is the third question. You can just say, we can easily show it by placing a wire vertically through a horizontal piece of cardboard on which iron filings are sprinkled. So when there is current through the wire, the filings or the compass needles, they will form what? A pattern or shape of concentric circles. So the circular line indicate the magnetic fields around current carrying wires form closed loops. So see these circles, it means like what? Closed loops, exactly like the lines or the field lines produced were around a bar magnet or a permanent magnet. You remember? Okay, we said that the field lines that runs from north to south, they form closed loops. So here we have the same thing, they form concentric circles. So these circles, they are like closed loops in the same way that field lines about permanent magnets form closed loops. Okay, the last point for today. So the strength of the magnetic field around a long straight wire is proportional to the current in the wire. What does this mean? So think about it. What means the strength of magnetic field, of this magnetic field produced, is proportional to the current? It's very clear. It means when you have a higher current, a higher amount of electrons moving, it means the magnetic field produced will be stronger. the magnetic field produced around will be what? Stronger. Okay, so girls, we can, if we want like to show the shape of magnetic field, if I don't want to use iron filings, I can use another thing, which is group of compasses. We can use group of compasses, like put them just around the wire, and you will see that their needles will all make the shape of a circle. They will align, so make this alignment. What does this mean? It means that the magnetic field, the shape of magnetic field is circles, is concentric circles, because always the needle align, it has the same direction of the magnetic field. Okay, so if I ask you how can you show, or how can you demonstrate the shape of magnetic field around a wire carrying current, you can say that by two things, either by using or by sprinkling like iron filings on a cardboard around the wire, okay, or you can say by putting compasses around the wire. The needle of the compasses, their needles will make the shape of circles. So a compass shows the direction of the field line. So always put in your mind the compass, the needle of the compass, it aligns with the field line. Okay, it has the same direction of the field line. It shows that the magnetic field around a current carrying wire forms circle around the wire. Each needle points in a direction tangent to the circle. Here they mean they align, just align, make alignment with this circle. Okay, if you reverse the direction of the current, the compass needle also reverses its direction. So here, girls, if the current was moving down, okay, if I reverse its direction, I make it move up. Okay, and also the direction of the compasses will change. So this is everything for today. Next time we will continue from this slide. Thank you.